Quantum computers make a lot of mistakes. Typical error rate for our operations is someplace between 1 in 1,000 and 1 in 10,000. So imagine trying to do a computation on a computer that, 1 in 1,000 calculations is just wrong. It's a ridiculously high error rate.
How does that error rate compare to classical computers?
I don't actually have the error rate for a transistor off the top of my head. It's something on the order of 10 to the minus 15.
Not very.
Enough orders of magnitude between them that it's just an unfathomable number. In practice on your classical processor, you typically don't do anything to correct for the errors other than maybe in the memory and the communication. So to do calculations today, we use something called error mitigation. And what that means is we run the same calculation a lot of times. We run small variants of the same calculation, and we can use that to statistically correct the errors. So even though each individual run had mistakes in it, at the end of the day, we can tell you what the answer would have been without those. That process is pretty expensive. You end up needing to run it an exponential number of times in the size of the circuit. And so you have the same overall scaling that you do with a classical computer, but the prefactor is better, so you end up winning. So this is sort of something that you can do to get into the game. We think it's going to work well enough that we'll show quantum advantage this year or next year. And that would be the point where we're doing something better, faster, cheaper on the quantum computer than we can do on a classical computer.
Is that what you mean by quantum advantage?
Yep, quantum utility. Something that you can't directly simulate, quantum advantage, something done better.
What is fault tolerance?
So error mitigation, we're correcting the errors statistically after the fact. Fault tolerance, you correct them as you run. And that is such a huge difference because it means the errors aren't compounding over the course of the computation. Fixing them as you do the calculation gives you ability to go to enormously larger circuits. That's that factor of 20,000 that we're talking about in 2029. With Starling is the difference between error mitigation, correcting after the fact, fault tolerance, correcting as you go. When you're doing this correction of the errors on the fly as you go, you actually need a substantial classical computer to work out what the errors were and to correct the calculation going forward, and you have to do that real time. So the classical computer has to be able to keep up with the quantum computer while you're doing that. For both the advantage applications and for these long-term fault-tolerant applications, anything you can do on a classical computer, you should do on a classical computer. We really want to reserve the quantum computer, this precious resource, for just the parts of the problem that it's really the only thing that it can solve. One application a lot of people like right now for advantage is something called SQD. It's a technique for simulating a chemistry. And in it, you use the quantum computer to choose what we call a basis, to choose basically how you represent the electrons in the chemical, but then you use the classical computer to actually work out what the energy levels are. And the reason why it works really well is the classical computer, when it does that actual calculation of the energies, does that calculation accurately. And so you don't need to correct for the kind of faults on the fly like you normally would. And so it's sort of an interesting example of error mitigation. In that, we're typically seeing runtimes on the quantum computers that are measured in hours and runtimes on the classical computers that are also measured in a few hours. But you can trade them off against each other a little bit. If you have a lower noise quantum computer, you can also make the classical part cheaper. You have a noisier quantum computer, you can make up for that by throwing additional classical supercomputing power at it. The way we correct the errors is we use more than one physical qubit to store each logical qubit. And that lets us do parity checks. We can compare the values on the physical qubits and see if one of them is flipped and fix it. The ratio of the number of physical qubits you need to the number of logical qubits you get, people call the rate of the code, and it's super important because the bigger that ratio it is, the harder it is to build the quantum computer that you want. If you look at the best error correcting codes people were talking about a couple of years ago for a useful logical qubit, you needed on the order of 1,000 physical qubits per logical qubit. To put that in perspective, this big machine behind me right now, that guy has about 450 qubits in it. So you needed something about twice as big as that in terms of number of qubits to store even one logical qubit. And one logical qubit is useless. I can simulate that on my iPhone. You really need about 100 of them before you're even doing anything interesting. So part of this announcement was an architecture for this computer built with a code that's about 10 times more efficient. And so that means for this code to store, in this case, a dozen logical qubits, they come in 12 packs, we need about 400 physical qubits. So again, referring to the system behind me, that's about a 12-pack of qubits. If I had about 10 of those systems, I would have something that's more powerful than the most powerful classical computer in the world. Now, to put that in perspective, this is the lobby of our building. I'm a physicist. condensed matter physics, studied like weird quantum states of matter. And I got into quantum computing to build that Blue Jay system. It was like the dream, this large scale fault tolerant quantum computer, the first quantum computer that can really run any quantum algorithm that you want to throw at it. And so it's always been kind of a game of, well, we're working really hard on the qubits. We're working really hard on small error correcting codes, all these little technology proofs for these error mitigated systems that they're computationally useful, but they're tricky to use well, in all honesty. And to have the technology have advanced so far that at this point in my career, I can say, you know what? I think that in 8 years, we'll have built that thing. That's just amazing that it's watching this entire field come to a pinnacle in the next decade that has me just delighted, tickled pink.
But so does AI play a role in the IBM roadmap? And if so, how?
So we talk about bits, neurons, and qubits. Classical computer, AI, and quantum as being what's going to power the future of computing. And at the end of the day, IBM and IBM research in particular is all about the future of computing, figuring out how it's going to influence all of our lives together for the better. I think there's going to be some really interesting stuff in quantum plus AI, actually. We talked a little bit about scaling and quantum advantage and being able to do something faster, better with a quantum computer than a classical. There are actually some very specific AI problems for which you can prove that a quantum computer would have an advantage. And that's sort of surprising to me. I mean, AI is very heuristic. It's very much, we do all this stuff and it kind of works, but it's really hard to prove why. And so beyond that, as we get quantum computers big enough to explore AI problems, I think we're going to see heuristics where quantum and AI play together very nicely as well. We use AI a lot in quantum. We talked a little bit about compiling quantum circuits, and it's a lot like a classical compiler for software, that we have an optimizing compiler. It finds places where you have redundant things inside of your quantum algorithm, simplifies them so that it runs faster. Right now, because we have such high error rates, if your circuit runs faster, it runs better. That's super important. And actually, we have a lot of AI-powered, what we call transpiler passes that go through and improve quantum circuits. So the reinforcement goes in both directions.
So the form factor and the footprint of quantum data centers is looking very different than traditional data center footprints.
Well, and it's looking very different from how anyone would have predicted it would have looked 2 years ago. That this advancement in the error correcting codes and the idea of building these modular fault-tolerant quantum computers is really bringing this from the kind of large-scale engineering you would think of like a space program or something like that into something that looks much more like a traditional IT sort of system.
You're at a dinner party. What do you say to people though? Why quantum? Why does it matter to me? Why does it matter to humanity?
I really like to pick on just one of those applications that I mentioned, material science. How do we simulate semiconductors, superconductors, strange novel materials? And the reason why I like to pick that one is, what are the ages of man named? We have the Stone Age, we have the Iron Age, we have the Bronze Age. That is how important materials are to us because it dictates what we can build. And so if quantum computers can bring forward material science so we can develop new, lighter, stronger materials, superconductors that work at higher temperatures, any of those things, just one run that invents one thing has the potential to change everything for everyone. And